Okay, so in this module, we're going to start talking about optical effects in semiconductors. And really, this means the interaction of light with semiconductors, either absorption or emission, and then the optoelectronic devices that are built around those principles. So first, we need to talk about absorption of photons. So we're going to represent our semiconductor simply first as just the conduction band and valence band. And the easiest thing to envision is the absorption of a photon with exactly enough energy to get across the band gap. So here's our band gap. So if this photon is absorbed, we create a hole in the valence band and promote that electron up to the conduction band. And the threshold is obviously exactly equal to the energy gap, but because the bands, if we look at the density of states picture, have a continuum of states both above and below the conduction band and valence band edges respectively, we can get a number of transitions for any photons that are bigger that can take place between those states. So any photons with energy greater than E gap can do this. It's worth mentioning that there's a simple relationship between wavelength in nanometers and energy in electron volts. So the number turns out to be 1240 over E in EV. And this comes from E equals hc over lambda. And you substitute in the values of Planck's constant and the speed of light there. So this can let you transform between the band gap wavelength and band gap energy easily. Okay, so the optical absorption turns out to be slightly different in indirect and direct gap semiconductors. So let's look at our k-vector resolved band structures for the two. So if we look on an EK diagram for a direct gap semiconductor, let's say gallium arsenide or gallium phosphide being great examples, and gallium nitride these days. So in these materials, it turns out that the absorption of light happens as vertical transitions. And let's look at why for a second here. So the photon comes in, takes a hole out of the top of the valence band, puts it right into the bottom of the conduction band. So we can look at the magnitude of the K and energy for photons and for phonons, which are going to have to participate in the next indirect case. So if we look at how far out this diagram goes, it's approximately given by pi over A, where A is the lattice constant of the semiconductor, which is about 5 angstroms or 0.5 nanometers. So this number, because nanometers are 10 to the minus 7 centimeters, is going to be of order 10 to the 7 to 10 to the 8th centimeters minus 1. And then the energy scale here, most semiconductors have a band gap of between, let's say, about a half an electron volt and 3 or 5 electron volts. So it's a few electron volts. Now let's look at a photon. If we write this slightly differently, we can find that for a photon, the relationship between the k vector and the energy is just c times k, so it's a linear dispersion instead of parabolic dispersion like this one. And it turns out that the value of c makes the wave vector of a photon something like about 100 times smaller on these EK diagrams. So photons can be envisioned as almost dead vertical transitions. Of course, they're tilted very slightly, but that distance in K space is very small. And I'm talking about something that has the same energy, the energy of a band gap transition. So this is the picture, which is rather simple for a direct band gap material. And I've drawn one transition here, but you'll also get, as I said, you'll get absorption. Any vertical transition like this can connect you from one part of the density of states to the density of states for the valence band up to the conduction band. And those will all look like this in this K-resolved picture. So now let's look at the indirect gap semiconductor. I'll just continue this axis over and we'll draw us a new. So this is direct and this is indirect. Now in this case, we have our K equals 0 or gamma point conduction band minimum here, but let's take the example of silicon. Its actual band gap involves the X point, which is at a finite K vector away from the origin. So this means there's no easy transition that involves a vertical photon transition. You can't conserve both energy and momentum unless you have another particle participating. So this is the photon here, and we have to have something that has a lot of momentum somehow. And we can either do a photon that's slightly bigger than the band gap, plus the emission of one of these special particles, which is called a phonon, and I'll explain what that is in a minute, or the absorption of a photon which is slightly smaller than the band gap, coupled with the absorption also of a phonon at the same time. So what's a photon and what's a phonon? A phonon is a quantum of lattice vibration. It turns out that the movement of all the atoms in the lattice is quantized, and it's beyond the scope of this book to really look into this, but a phonon can be envisioned as a particle of vibration of the lattice. Whereas our photon is a particle of light. So it turns out that a phonon is almost purely momentum on this scale, meaning that the momentum is very big for a phonon, but its energy is very small. So its energy might be measured in something like 10 millielectron volts, whereas a photon might have 1/100th of the momentum, but 100 or 1,000 times bigger energy. So a photon is almost pure energy. Or a vertical transition. A phonon is almost pure momentum, or a horizontal transition. So in an indirect material like silicon, you put those two together and you can get yourself over to the conduction band minimum at X, conserving both energy and momentum at the same time. But what this means is that you have to have three particles participating. You have to have an electron, you have to have a photon and a phonon all at the same time. So the probability of these processes is very much reduced, something on the order of about 100 times weaker. So let's talk for a minute about how we measure the strength of optical absorption. So we can look at how electromagnetic energy or light is absorbed inside a material. First, let's just look at a real picture. If we have an E&M wave traveling through air, its amplitude stays the same versus distance. But then if it crosses into a medium that absorbs it, its amplitude will decrease exponentially as it goes in. So we'll see this amplitude go down like this. And sorry, I missed with my line there. Looks more like that. So the amplitude has a certain exponential decay, which we characterize by the absorption coefficient alpha. And it turns out it's more useful to define this in terms of intensity. What's called the Beer-Lambert law says that the intensity as a function of distance into the material equals I naught, which is the value at the surface, times exponential to the minus alpha times distance x. So we can look then at the absorption coefficient versus photon energy to sort of get the total effect of all these band structure details for every different semiconductor. So usually we have to present this on a log scale because it turns out once you hit the band gap, the absorption rises very steeply, especially for a direct gap semiconductor. So the value somewhere within about a half an electron volt of the band gap itself, a typical value is about 10 to the fourth in inverse centimeters for a direct gap material. Now for an indirect gap material, that rise is a lot slower. And so you see something that rises more gently. Eventually it'll reach the same very high values in the 10 to the 5, 10 to the 6 range, but that's at very high energies above the band gap. And you'll see the onset of absorption actually below the nominal band gap because of this transition here involving the absorption of both a phonon and a photon at the same time. So this is the indirect materials behavior, and this is the direct gap materials behavior. So a typical number to use for estimation in an indirect material would be about 10 to the 2 inverse centimeters, somewhere right around the band gap. And again, that's about 100 times less than for a direct gap material. Now the last thing to mention here is that the absorption coefficient actually turns out to be the emission coefficient because quantum mechanical transitions are reversible. We can immediately see that if we start with two excess carriers and they recombine radiatively, for example, it's actually the time reverse of the absorption process. And we'll go into that a little more when we get into discussing LEDs.